Okay, hello everybody. Today I would like to show you our presentation about the multimodal analysis of speech and gaze fusion in mixed reality for the detection of neurodegenerative disorders. Here, I would like to present to you and show why we're using such device for the healthcare setting. So we use it mainly because we have the possibility of retrieval of multimodal aspects. So for this experiment, we use gaze and speech, but in the future, we would like to extend it also on the head movement and head's placement. So you would have more and more data. But for now, we are using those two because they are one of the most important regarding how we are actually perceiving the Parkinson disease. The device itself is having standardized geometry, which is a high value because we have a constant mix distance. So microphones are this in particular manner, and also we have a high gaze detection retrieval. We are using those two also because we have the ecological tasks. They are easy to actually establish in people with in elderly age. And they are very willing to actually use those glasses because they are actually willing to know new devices. So actually they are participating very well. Also regarding these devices, they are very nice because they are lightweight and repeatable. So we can use them easily in the clinic setting, but in the future also in the home monitoring. And we are fusing the gaze and voice itself because first, speech. We are seeing that for the people with Parkinson's disease, they are having reduced rate and verbal outputs are common in Parkinson's disease. And also regarding the gaze, the oculomotor changes can affect the fixation stability and the possibility of actually scanning through the pictures and other things that they are seeing. So basically, we thought about that maybe we can fuse this and try to establish the information. Are you describing what you are actually looking at? So from this perspective, we are going for interpretable multimodal behavioral biomarkers. And for this study, we used our task, which was basically describing the main image, as you can see on the slide, which they had 30 seconds to actually describe. It was in Polish, so it's very important because we are using this particular language to establish the information. In our cohort, we used 10 people that were on medication and 18 people that were totally on the healthy control. As you can see on the table down there, maybe it's not interpretable for you, but in fact it's usable because we are through it. You can actually see when you research and get information that we are using the people that are having mild tendency regarding the Parkinson disease. So from this perspective, we are trying to actually retrieve some kind of subtle changes that can actually be established future as a biomarkers. So this is a very important from our perspective. And our pipeline consists of, let's say, 3 branches. First is the eye tracking the data. So we are retrieving the gaze feature set. We are using Chrome microphone input data to establish the voice feature set. And also we have the alignment scoring. So basically fusing the data. So identification where someone was actually looking at and the semantic analysis, what was actually set. And then we are getting the alignment scoring. But I will dive into more details right now. So first, we have the voice stream in which we are having the audio. We are having the Whisper X actually start to get the timestamp and all of the information from the audio. We are using the Spacey Polish NLP toolkit to actually retrieve particular information. So, for example, we are retrieving the MLTD, the TTR, the tokens, the unique tokens, the fluency, so words per minute, and the pulse-based temporal metrics computed from word time. So for now, we are going for more like speech and less by voice itself. And as you can see on the image on the right side, on the figure, we can see that people with Parkinson's disease tends to speak slower and produce fewer words actually. So basically they are not having this kind of energy to establish something meaningful through the image. So this is the first, let's say, indication that this kind of behavior is happening. Regarding the gaze stream, we are preprocessing by smoothing with Sawicki Golay to reduce the jitter, derive velocity and acceleration from gaze coordinates, detect fixation as low velocity periods, so around more than 10 samples, and compute fixation per second plus summary about the kinematics. So basically, as you can see on the image right here below, we subdivided this into grid 2x4. So basically all of the needed information around this kind of particular cells was actually established, so semantics, and basically these people were going through all of those cells and try to actually describe what they are seeing, and we calculated those gaze features, and on the figure or on the right you can see that we have the fixation rate, which is also pretty much lower than the healthy control. So this is also the next indicative thing that we are seeing through the gaze fixation per second. Lastly, we have the fusion, which is basically the fusion of those two. So where they are looking at what they are describing, we used 2 seconds beams for this. So basically we got around 20 frames to establish. We tested 1, 2, 4, 8 seconds, and we saw that the 2 seconds works the best. For each beam, that we are determining the primary ROI, so basically where the participant were looking at. Free experts rate if the speech matches, so we are getting 1, 0.5, or 0, and we are establishing the median as our main value. So if there is a clear match, so when someone's actually describing everything in a great manner, he or she was getting 1. If something was partial, so for example, in some close part of the image or something like this, this participant was getting 0.5, and if there was like a total mismatch, this participant was getting 0. This helps actually to all of this idea helps to get the direct behavioral readout and captures coordinates deficits beyond the raw speech and or raw gaze, and can be used as a next feature in the downstream models. And as you can see on the weighted alignment accuracy, we are calculating this as a sum of the clear matches, and we are calculating the half, as it is stated in here, by the amount of 0.5, and basically so dividing it by the amount of all of the frames that we have. Regarding the first results, so the gaze speech alignment is lower in PD. As you can see, we know that our cohort is not big enough to actually establish like a very strong evidence, but still we are having this tendency that the people with PD are actually having lower accuracy regarding the description. So basically they are not using unique approaches to describe, or they are having this kind of problems regarding the fixation and their gaze. So this is the first thing that we saw. Second thing is that we calculated our machine learning models with k nearest neighbors, and we used the top k features. So in that manner, we used 7 features, and we saw that first, the amount of part of speech, so pronouns per 100, in total were actually in the different directions. So basically the people with Parkinson disease, they were tending to have a higher values, which is actually possible because of our Polish language, which is actually using the different wording. And regarding other features, so word means per total, voice or unique tokens, and we also have gaze fixation for a second, so we also have the gaze features, tokens orientedly, we are seeing that there are like a shift to this kind of negative effect size on the Cliffs delta. So we are seeing that there is kind of also division between the healthy control and Parkinson disease. And lastly, if we are compacting the features and how they are separating themselves, we use the centroid distance and the nearest centroid balance accuracy to actually establish the information. And as you can see, if we are using also the alignment scoring, we are getting the balance accuracy which is higher. Our confidence interval actually shifting to the higher values, and the distance itself is also pretty much established as a good value. So in that matter, we are seeing that alignment scoring is actually helping, and we are getting pretty decent results through this type of approach when we are fusing those two features. So in a summary, MR can actually capture synchronized gaze and speech during an ecological task in 1 minute. PD participants show briefer speech and fewer stable fixations, lower gaze speech alignment, and we are getting a compact interpretable feature set yields a meaningful separation. So basically, we are getting the information that adding alignment is actually helping us, but we know that our main limitation is a small cohort, which is 10 PD, 18 HC participants, and a single stimulus. In the future, we would like to have a bigger cohort using acoustics, because for this task it was harder to retrieve meaningful acoustics, and a richer gaze. Thank you very much for the attention, and I hope that we will see each other on the conference itself. Thank you very much, and hear you soon. Bye.